Welcome everyone! Today we will talk about recursion. I expect most of you to already be somewhat familiar with it, but for the ones who have never heard about it before, here's a definition. Recursion occurs when a thing is defined in terms of itself or of its type. The most common application of recursion is in mathematics and computer science, where a function being defined is applied within its own definition. You can tell this is a really nice description. I took it from Wikipedia. Let's transform it though into something simpler. Recursion is, in essence, solving a problem by solving the same problem but with a smaller size first. This is by me and some other people probably. The key idea is to use the solution of the smaller problem to build up the solution of the larger one. Let's look at an example, the Fibonacci sequence. Can you notice some relationship between the numbers? Any number in the sequence is the sum of the previous two. Now let me show you how just using that relationship and knowing the first two numbers in the sequence, one can recursively compute any Fibonacci number. Say we want to compute the fifth number. Well, it is nothing more than the sum of the fourth and third Fibonacci number. But since we don't know any of those two yet, let's figure it out. Since the procedure is the same for both branches, we will focus on the left one. The fourth Fibonacci number is the sum of the third and second number, and the third number is obtained by adding up the first and the second. At this point, we can start working upwards. We know that the first Fibonacci number is 0, and that the second one is 1. Then, we can compute the third number, then the fourth, and finally we have the answer for the fifth Fibonacci number, which is, ironically, 5. If one were to write a Python function to get the ith Fibonacci number, it could look like this. If I is 1 or 2, we can give the answer directly. But for any other number, we employ the recursive relationship. This part here is what we, nerds, call the base case. In this state, the problem is so trivial that we can easily code the answer. The other section is called the recursive step. It's that leap of faith that should take us a little bit closer to the base case. Let's take a look now at a more complicated problem. We define a square as a number whose square root is an integer. For instance, 9 is a square, since its square root is 3. However, 8 is not, since its square root is not a whole number. The problem states that each number can be represented as a sum of non-decreasing squares. Let's take 9 as an example. Since it is itself a square, then 9 is one of the sums. But we also have 1 plus 4 plus 4, 1 plus 1 plus 1 plus 1 plus 1 plus 4, and finally 1 plus 1 plus 1 plus 1 plus 1, etc., etc. When I had to solve this problem for one of my courses, it took me a long while. To come up with an answer, I took inspiration from Reducible's video in 5 simple steps for solving any recursive problem. Links in the description below. Firstly, let's flip around the sums, so that we end up with non-increasing squares instead. This is way easier on the eyes and more intuitive, since it directly shows us that we should decrease the given number one square at a time until we reach 1, our base case. The question is how. Let me display the sums for several numbers and give you some time to come up with a recursive relationship. I encourage you to pause the video, give it some thought, and come back later. Let's take a look at the sums for 9, 5, and 8, focusing on 9. 9 is itself a square, so there is a sum already. Then, there are two squares smaller than 9, 4 and 1. Let's start with the latter. For that part, we are interested in the number of sums of 9 minus 1, 8. There's a tiny detail though. We cannot use a square larger than 1 for such sums, or we would be violating the non-increasing squares constraint. Thus, there is only one sum we can use. For the other square, 4, we are interested in the number of sums of 9 minus 4, 5, starting with a square no larger than 4. And as you can see, both sums of 5 are valid. We can now write a Python function for this problem. Note that we will need two parameters, the number itself, I, and the limit regarding the first square in the sum, so that we can avoid violating the constraint. If the number or the limit is 1, we know that there's only one sum, in other words, 1 plus 1 plus 1 plus 1 and so on. Otherwise, we can employ the recursive relationship which we have just discussed. If the number is a square and we are allowed to use it as the first element in the sum, we increase the sums by 1. This latter check is important because in a scenario where we want to compute the number of sums of 9 with 4 as the limit, we should not take 9 itself into account. Now, we iterate k from 1 to limit plus 1 or I, whichever is smaller, since it doesn't make sense to consider limits higher than I. Also, note that the endpoint is excluded in Python. This is why we wrote limit plus 1 instead of limit and I instead of I minus 1. Then, if k is a square, we increment sums by the number of sums of I minus k, with k as the limit. One should note that there are more clever and faster ways to implement the solution. However, that's out of the scope of this video. Recursion is a truly beautiful thing. It is applicable to many areas and concrete problems. One of my favorite traits is that it's not a mechanical procedure which you can simply adapt from use case to use case. Each problem requires you to find its unique recursive relationship. And as you have seen, this can be quite complicated sometimes. If you want to learn more about recursion, there's a small collection of videos in the description below. Thank you so much for watching and see you in the next video.